Broadcasting from the beautiful Spelman porch, going through Newton's third law. We're talking about force pairs. So again, Newton's first law was dealing with inertia. Newton's second law is our force equals mass times acceleration, which is still kind of about inertia and the relationship between forces and acceleration. And Newton's third law talks about what happens when forces bump into each other. So we're going to try to answer the questions: what is Newton's third law of motion, and how does it describe action and reaction situations? Don't really have any new vocabulary for this one, so we'll move along. Newton's third law can kind of be summarized: for every action force, there is an equal and opposite reaction force. You've probably heard versions of this where people say for every action, there's an equal and opposite reaction. Well, that's not exactly what it's talking about in Newton's third law. It's actually every action force, there is an equal and opposite reaction force, right? The key thing to keep in mind is this is explaining two forces on two different objects. So this is not two forces on the same object. So like with Newton's second law, we looked at an image of an object sitting on top of a table, and there was a force pushing down and a force pushing up. We were actually talking about two forces acting on two different objects that kind of come in collision with one another. It's usually, or they are just basically, they don't have to be a collision, but it's one object kind of acting on another object, pushing it in some way, right? So the idea here is, if you have a can, if we're kicking a can, this is a perfect example, because Newton's third law explains that there's two forces on two objects. So in this case, there's an action object, which is the foot, and there's a reaction object, which is the can, but there's a force from the foot onto the can. Likewise, there's a force from the can onto the foot. Now, again, the can's not going to react without being kicked in this case, but if there is a force acting on a can, there's also a force acting from the can back onto the foot. All right. And so again, if you look at this, you're like, wait a minute, that doesn't look equal, because Newton's third law says there's equal and opposite forces. And so what you have to kind of keep in mind with this is always, 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 and one more time, always, the forces are equal. So the force on the can and the force on the foot are equal. What's different, though, is to remember that a force is a mass times an acceleration. And since the mass of the foot is different than the mass of the can, then we're going to get a corresponding difference in acceleration. So hopefully remember, if the mass is bigger, then the acceleration is going to be smaller. If the mass is smaller, then the acceleration is going to be bigger. So in this case, with the foot and the can, the big mass doesn't change its speed very much. So when you kick something, you barely even notice that the speed of your foot changed. What we notice is the speed of the can changing. The can is really, really small. It has a small mass, so it's going to end up having the bigger acceleration. So try to keep that in mind with any examples that you're looking at, is that the forces themselves are equal. The results that we see that aren't equal are going to be due to the acceleration changes that we see due to the masses. All right. So do these forces cancel out? Well, no, they don't cancel out, because the forces are not acting on the same object. There's a force on the foot and there's a force on the can. Those forces are equal. They're in opposite directions, but they don't cancel out because they're not acting on the same object. So it's not that we have a net force of 0 in this case. So the can will cause the foot to decelerate. The foot will cause the can to accelerate. The forces themselves don't cancel out. Apparently I copied this slide again. So oftentimes you're given examples and you just want to look at and say, what is the action and reaction force of something where we see it? So in this case, if we have a car driving down the road or a car on rocks, kind of the action in this case is that the tires push on the road, or the push on the ground in this case. So if the tires are pushing on the road, the reaction force is the opposite of that. And so in this case, it's the road pushing on the tires. These forces are going to be equal, but we're not going to see an equal acceleration. If you think of the road being part of the earth, then we don't see the road accelerate at all effectively. We see the car accelerating. So because the car is so much smaller, it's going to experience the greater acceleration. When we have someone swimming in water, if the swimmer is causing the action, the swimmer is pushing the water, then the reaction, flip this around, the water is pushing the swimmer. Those forces are going to be equal. The water and the swimmer are not going to have equal changes in acceleration, though, because there's different amounts of mass involved. So again, what we see is not a difference in the forces. What we see is a difference in the acceleration. So try to keep that in mind in any kind of example that you're given, or you're trying to being asked to analyze it in terms of forces or mass or acceleration. Forces are always going to be equal, but the acceleration might not be if the masses are going to be different. So again, if a big object hits a small object, the big object's not going to accelerate very much at all. The small object's going to experience a lot of acceleration. That is what we see, right? So what about me and the Earth? Well, if the Earth accelerates me downward, doesn't that mean that I accelerate the Earth upward? Yep, sure does. So again, why do we not see the Earth accelerating upward? If I jump up off the ground, why doesn't the Earth rush up to meet me? Well, the Earth's a little bit bigger than we are. So again, with the Earth being so massive, it's going to experience a tiny acceleration. Compared to the Earth, we're really tiny, so we're going to experience a large acceleration. So you can't have an increase in both mass and acceleration. As one gets smaller, the other one's going to get larger. So the masses are so different that we don't notice the acceleration of the Earth because the Earth is a large object, therefore it's not going to accelerate very much at all. And that will do it.